have box set up, and we've done a diagram that shows what we're going to do to connect our first Verilog project in Vivado. We can get started by invoking Vivado and working on the workflow that I'm really wanting you to focus on. Okay, so as I mentioned, we've set up Box, all right, and so the quick links for me are under the lab. I have a place for lab 1, I have a place for the report, and this is where I'm going to put the project when I run Vivado. All right, so I have that all set up. I know how I'm going to connect the project because I've drawn a diagram, and so I have a pretty good feel of the top level module and the internal module that's going to do the functionality of what we're trying to do. Okay, so let's run Vivado, and you can start searching and it'll come up and you launch this app. Of course, it's a big app, and with this video, I'm going to edit out some of the really long delays that you get, but you should be patient. Even with the little tiny project, several things have to happen in order to run this big piece of software and to create projects and to make everything that needs to happen under the hood happen. Okay, so you see Vivado come up, and we are going to do our project. So create a project is the first thing you click on, and you'll get a little window saying that that's in progress, and then a little wizard gets invoked. This takes you through the creation of a project, so I'm going to hit next here. And now I want to make sure that the project location is where I expect it to be. If it's not, I can browse to the location that I want, but this is what I'd set up before, and so that's already present in mine. If it's not in the right place for you, for example, it's not in your box drive, and it's on a local drive in the computer lab, you'd probably want to move that over at this point and make sure you have the right place. Okay. I like to create a project subdirectory because it keeps the project in a certain place, and sometimes projects get corrupted in Vivado, and I've had instances where I just said, I'm just going to start over and delete the project and begin again. And so that way I have a clean folder for that to happen. All right. You can name your project, and in this case it auto-named it. I'm just going to go with that. And you could choose a descriptive name of your own if you want. Okay, so we're ready to go. I hit next. This is a registered RTL project, Register Transfer Language project, and we are not going to specify sources at this time. This is sort of the default screen. You'll always hit that and go to the next thing. Okay, next it's important to remember the target board, especially if you're going to connect the basis board to your computer so that you can program it. Sometimes we're just doing a simulation and we don't need to worry about the board. We're not going to use the target, but in this case, that's the whole point. We want to do something quick and easy and get an early victory. All right, so we need to specify the target. It's basis, BASYS. It's good to know how to spell this so that you can do a search. Another tip that I want to have for you, it's real tempting to click on this blue highlighted link, but you don't want to do that because it'll just bring up a web page that shows the description of the board. So click in the white space right next to it, and this will be highlighted in blue, and then you can hit next and finish, and we will create a project with the correctly targeted board. Okay. So at this point, it takes a while to run through that, and so be patient. We'll wait for it. Okay, and it's finally finished. And at this point, we're ready to start adding design sources. Okay, so the first design source we're going to do is the inner module that has the functionality where we're going to invert the switches. So just as a summary, we want to connect the switches to the LEDs, but the sort of default program that runs with the board already has the switches connected to the LEDs. And so when you move the LED to the up position, when I move the switch to the up position, the LED comes on. So let's flip that around where when you have the switch in the down position, the LED is on. When you move it up, the LED turns off. So it's a pass-through kind of connection like we talked about in the previous video. And let's get started with adding the design source for that. So let me go back and explain this. I clicked this label here, made that highlight in blue, and then hit the plus button. And then that gave me the default correct value for creating a design source. Okay, so I'm going to hit next. And from here, I'm going to create a file. I'm going to call this pass invert. Okay. All right, so let's finish that. And what's going to happen next is there will be a little interface that lets you set the inputs and the outputs for the ports for the module. Okay. In many cases, we'll just default out of that. We'll cancel and we'll define our own module setup. But I think, as a first start, it's good to go ahead and let Vivado generate the syntax that you need. Okay, and so for a port name on the input side, all right, I'm going to have an input like I did with the block diagram for the inner module. It's going to be a bus, and it's going to be 16 bits, 15 down to 0. Okay, this port name, I could have made it anything. I'm calling it XN because the X meaning you think of X and Y, but X is the input, and then I'm going to have an output Y out. I could have named these differently because these are inputs that I'm designing on my inner module. My outer module will have some constraints, and we'll talk about that as we get to it. All right, so the output module is 15 bits, 15 down to 0. I've got this set up with an input and output, port names. I'm ready to go. Hit OK. All right, so again, that takes a little while. You can see it updating, and then if you hit the down arrow, you'll see the name of the file, and you can click on that, and it will open it up. And these are just text files for the code. All right, so if you could look through your directory structure and find pass_invert.v, and you could actually open that with Notepad and see the code that's written there. Okay, so initially these are some comment lines. You could add your name here in the comments. We're not going to worry about all the details yet. We'll talk about this more at some other time when we look at this timescale parameter. Okay, but let me draw your attention to what the template generator came up with. We're making a module, so we have the module keyword. We have the name of the module, pass invert. There's an open parentheses, and then later a closed parentheses with a semicolon. Then we have inputs. I called XN as one of the inputs. We have outputs. Y out is one of the outputs. But I noticed here, I must have fat fingered this. 0 down to 0, that's not what I intended to put in. Okay, so I happened to catch that mistake. Be watching for that. You might have seen it, back when I did it. But all right, 15 down to 0. I need the same number of bits coming in as the same as going out. All right. So from here, I'm ready to define the functionality of this pass invert module. And so I'm going to assign, and I realize you don't know the syntax of Verilog yet, but I'm just telling you, assign is the command that we use to connect essentially Y out to XN, right? But this is not quite right. This would make the switch directly connected to the LEDs, but we want to invert things, right? We want the up to be off and down to be on. And so we're going to use an inversion operator in Verilog. That's just simply a tilde. And this would give me a bitwise inversion of XN. All right, so keeping it simple so we get an early win. This is, we talked about that in the original diagram that I made. This is pretty simple. This is what we have as an inner module. So I'm going to save that. All right, the next thing I'm going to do is I'm going to create the wrapper module that lets me communicate what all the connections need to be between the external pins and switches and things on the board to the internal gate configurations and logic configurations that are generated by Verilog. Okay, so I'm going to add that source. I'm going to create a file. I'm going to call this top to make it clear that it's the top of the pass invert circuit that we're working on. Okay, and so I'm going to finish that. All right, so here's where we get to the point where we've drawn a diagram where we know we have switches as an input. All right, this is constrained. This variable name can't be just anything you want. All right, the constraint file is a file that lets the whole system know what are the variable names for the switches and what pins are those connected to. How do we make everything get connected properly with this software? All right, so SW has, it has to be exactly SW. It can't be some other name that you come up with for the switches. And again, this is 15 bits. I'm sorry, 16 bits, so 15 down to 0. All right, the other thing that we're going to do is we're going to connect the LEDs, and that has to be LED, not LED with an S, LED exactly right, so that's what shows up in the constraint files. All right, and it's an output, that's important to know, and that's why we did our diagram. We want to know, what's an input, what's an output. All right, it's a bus as well, 15 bits, 16 bits, 15 down to 0, which is 16 bits. Okay, and I accidentally clicked here and it gave me something else, but if there's no variable name, that's not relevant. Okay, so we've got that done. I can hit OK, and it's going to update that, and we see a new item showing up in our design sources. So I click on that, and you see with the editor that gets opened up. So again, you can put your name, add any comments if you want at the top of the file. Okay, so we're seeing the same structure. So I want you to pay attention to what you're seeing and try to take note of the notation, try to remember it. All right, module, it's a keyword saying we're going to make a new module. We have a name of the module, open parentheses, close parentheses with a semicolon, input list. All right, here's the notation for vectors, 15 down to 0. All right, and then here's the notation for a vector for the output LED. All right, so we're ready to make the connections. All right, but connect to what? Well, that's why we had this diagram. We knew that our top level module its sole purpose is to be the interface between the logic that we're creating, which in this case is very simple, to the target hardware. All right, so that means we need to know the name of the module that we already created. Pass invert was the name. I can have a label because I can instantiate several versions of modules if I need to. We'll do that later on, but we just have one module we're trying to instantiate, and so you give it the model name and then some label. So I'm going to call it PI for pass invert. All right, and then you could make the connections in a couple of ways. All right, so the first way I'm going to show you is we know from the pass invert module that we wrote, XN is first, and we want switches to be connected to XN, and we want Y out to be connected to LED. So this would do the job. Okay, this worked easy because I could easily remember the order, and I didn't have to know the names of the variables that showed up in pass invert. I knew that XN came first and Y out came second. Right, but if you had a more complicated module that you were writing, it gets tricky to remember the order, and you want to make sure that you get the names right, and so you can pass these parameters by name instead of by position. Okay, we're going to keep the same position order just because there's only two of them, but you put the dot, a period, and then the name, and that lets the software know that dot Y out should be connected to LED, and dot XN of the instantiated model should be connected to the switches. All right, so that's it. That tells me how to make the connections, and I've instantiated the inner module, and I have this set up and almost ready to go. All right, so we're going to save that. So the next thing we need to do is we need to let the system know where are this, what are the switches, how does that work, what pin numbers are used, and so we have to add constraint files to let that be known to the system. So highlight that in blue, hit the plus button, and you will get a default button of add/create constraints. All right, so we'll hit next here. And we already have the files. If you remember, there's a folder that I had saved on Box. You would need to download these constraint files to your own workspace from Canvas. I have them uploaded on Canvas. All right, so you may not remember my directory structure, but if you go up one level, you get to a folder that has constraint files in them. All right, and we're going to look at the LED, and so you see it's just a bunch of code that sets the ports with pin numbers and variable names. So package pin U16 LED 0. All right, that's why LED has to be labeled LED. Okay, all right, so just as an example. All right, so we use LED and switches, so I hit the control button, select both of these, and then, okay, you could add them one at a time, but I added them both at the same time. All right, so we have the switches and the switches and LED constraint files. Let's finish that. All right, and at this point, our design should be ready to go. All right, now sometimes you're going to want to run a simulation first. In fact, that's the general design process. Is you make modules, you run simulations, make sure they work before you try to target that to hardware. But our goal was something quick and dirty and getting it working on the hardware. So at this point, let's first of all take a look at the schematic. Okay, so the schematic, you can look at the RTL analysis and take a look at the schematic that the software is interpreting from your code. All right, this is not a necessary step every time, but I like to open that up just to see what it looks like sometimes. And here's what we have. All right, so I'm going to recenter this. All right, so we had instantiated our inner module, pass invert, and we labeled that PI. So that label shows up here. This tells it what module that we're doing. I can click on this plus button, and it shows the internal structure of the pass invert module. So we know we have 16 bits coming to the input and 16 bits coming to the output, and we are simply inverting every bit. Okay, so this schematic illustrates that. So I'm feeling pretty good about that. All right, and so from here, I can hit run synthesis. All right, and so these next couple of steps are to get to what's something called a bit file, and the bit file is what actually gets loaded and helps you program the connections that need to be made on the target hardware. Okay, so at this point I wanted to show you in this upper corner you can kind of get a status of what's happening. This is running the synthesis design. All right. Another thing you can do is hit project summary, and it lets you know what stage you're at. Okay, so we're doing the synthesis first, and the next part of the workflow is to run the implementation. And so we'll wait. I'll try to edit out some of the waiting to make this video a little bit shorter. Okay, so at this point, it looks like the synthesis successfully completed, and it gives you a hint for the next step. The next step is to run the implementation. We hit OK. And again, we can look at the upper corner to get some type of status update. Okay. So you see the circling in the upper corner, and then also there's an indication of the implementation running. Okay, again, this always takes a while to do. And that's why you want to be careful and try to be not make errors, so you don't have to wait through this process. But it is somewhat lengthy. Okay, so it said that completed. There's some warnings, but we're going to hope for the best at this point. And the next thing we need to do is generate the bit stream that lets us program our target device. So we click OK on that and generate the bit stream. And again, we will wait a little bit to make sure, or wait for that to happen. And we get an update here running right bit stream, and it also shows up in this upper corner. Okay, so while that's finishing, we're coming close to the end of the line of what I can show you in this video. The next step, once you have a bitstream file, is to open the hardware manager to program the board. But my problem is, I don't have the board physically connected to my Mac. Remember, I'm running a Windows machine that's located in my office, and there's no board connected to that. And so I can't show you those steps because I don't have target hardware in place. But basically, you're going to open this hardware manager. You can click on Open Target, and it'll generate a different screen, and you'll see some stuff that's in green at the top, and eventually hopefully your board will open. There's been times when I've had a little trouble with that and have had to close out Vivado and restart it if you throw some error messages on opening the target. But hopefully that goes cleanly, and you see here it says I've got a bitstream generation was successfully completed. Your next step would be to open the hardware manager. And again, that's not going to work for me in the way I have things set up. So from there, I think it's a little bit obvious what to do. You open the hardware manager, you look at the top of the screen, and eventually something shows up that says Program Device, and you hit that button. And generally, the good news is that step usually happens pretty fast, so you'll know whether the hardware gets programmed properly, because you'll be able to flip the switches and see if they do what you expect them to do. Okay, so that wraps it up for this walkthrough video of the project, and hopefully you'll get an easy win. I'm looking at the video time, and in real time it took me 27 minutes. I may edit out some of the periods where we're waiting on the Vivado software to run, but this gives you an idea of what the workflow is like And so it's sort of a minimum time of 30 minutes to get a project running from the ground up. And then, of course, if you have more complicated logic, that extends that time. Okay, so hopefully you found this interesting and helpful.